Today, we are going to go over the one sample t-test. Basically, we're going to go through the steps of phantoms as we did with our one sample proportion, our two sample proportion, and a kind of modified version of phantoms when we did chi-squared. So we are just going back through the exact same thing we did when we were dealing with categorical data. However, now we are dealing with quantitative data. We're dealing with means. Big key thing we talked about when we were doing the intervals was how important it is to make sure you're using the correct symbols. So when you're defining the parameters for a t-test, it has to be mu. Mu is equal to the true mean of whatever your parameter you're trying to find a probability of is. H is going to be stating the null and the alternative hypothesis. Yes, you have to have both. One thing I do want to remind you of is we are saying mu is equal to some value. So you have to include this initial mu. A lot of the times on previous tests, I had students who would just say null is equal to 5. It has to be the mu is equal to 5. We're saying the true mean is equal to 5. Just make sure that is something that they will be picky about on the AP exam. Don't want that to be one of the reasons why you potentially lose points. So the null is always that they are equal to each other. The alternative depends on what they are claiming or believe to be happening. So it could be less than, it could be greater than, or it could be, is there a difference at all? They sometimes phrase it in that way, or does it follow the national mean, or does it follow what we expect to happen? That's when we're doing the difference between the true mean of the population and our estimation of the mean. So null and alternative. Assumptions and conditions are going to be exactly the same from our confidence interval. So we have to go in, we have to check, is it random? We have to go in and check 10% condition. And remember, sometimes we deal with experiments and where we don't necessarily have we don't necessarily have the capability to do a random sample. In that instance, we could say treatments were randomly assigned, and we could also go in and say the results for each participant are independent, because basically together randomization and 10% condition are checking the independence assumption, just making sure that all of these results have no bias or influence that we can notably see. Then we have our nearly normal condition, and this is the one where you have many options for how you can satisfy it. First, and most ideal, it was stated in the problem, meaning they told you it follows a normal distribution. That's usually great because you can just say normal, approximately normal, stated in problem. Second best option, central limit theorem, which is as our sample size gets larger, specifically greater than 30, we can assume that it's approximately normal. Third option, which is not always the best option, is a visual representation. You are doing a histogram or a box plot, and you're trying to see if there is strong skew or outliers. And you will always have to include a sketch on your FRQ. Now, in terms of AP exam, I do not think that they would make you do a visual representation just because it leaves too much room for error, too much room for miscalculating or mistyping a 10 instead of a 100, therefore throwing off all of your data. They, for the most part, will not have you enter in tons and tons of data into your calculator just to kind of help refine their possible answers that they have to go through and grade. And another thing, if you do happen to get a sample size that is less than 30, you can only do T procedures when we have no outliers and no strong skew. And basically, that kind of falls right in line with us having to do a visual representation. So we're through PHA down to N, naming the method. It's a one sample t-test. Now, as I always do, I'm going to show you how to do this by hand, and then we're going to talk about how to do it in your calculator. The general formula for a test statistic, a z-score for proportions, and a t-statistic, sometimes I call it a t-score too, for t procedures, is we get our statistic. It's equal to statistic minus parameter over standard deviation, x minus mu over sigma. Now, in the realm of a one proportion t, oops, that should say z. Caught my mistake early enough. This should be a t-test. Sorry, guys. Copy paste. Sometimes it's your best friend, sometimes it's your worst. Um, so how we calculate this. Our statistic, remember statistic has to deal with sample. They both start with S. Our statistic is X bar. This is going to be given to you. This is our sample mean. Then we have our null proportion, which is going to come from the question. Generally, it will be the expected claim that they say they think is occurring. Like they say the national average is 50%, or the national mean is 50. Mu naught would be 50. S is our sample standard deviation, and then over the square root of n. And the reason why we do have n in our calculation for standard deviation is we have to remember when I'm taking the mean of something, I'm not just necessarily getting one person's value. I'm getting multiple people's values added together and averaged. So we do have to take into consideration how big of a sample did we take. Taking a sample of 10 is very different than taking a sample of 100. So that's why in anything we do with means, we are typically dividing by the square root of n, just to kind of account for the idea that I'm taking more than one person's sample. So now we are going to obtain a p-value. This is the exact same thing we did when we were working with proportions. Depending on what your alternative hypothesis is, if it's less than, if it's greater than, or if it's not equal to, we have a different type of shading. And for our shadings, this would be a one-tail test. This would also be a one-tailed test. And this would be a two-tailed test, just to bring back some terminology. So the one-tailed tests are nice and easy. All you have to do is calculate your test statistic. If it's less than, we are shading everything less than that test statistic. And in our calculator, we go to second vars number 6, negative infinity to that value. Degree of freedom is calculated exactly as it was for confidence intervals, n minus 1. If I'm saying I think the mu is greater than the claim, it's going to be everything shaded above that test statistic. And then I do t to infinity when I do second vars number 6. The special case is when you're doing a difference alternative. So that is a two-tailed test. And the nice thing about two-tailed tests is they have the same probability in each tail. So this area is equivalent to this area. Therefore, I only have to find one, and then I just have to go in and I have to multiply it by 2. So pick whichever side you like. You could do negative infinity to that negative t, multiply it by 2. That is the only way to do the p-value. One thing I will make note of here, in our calculator, when you do stat tests, the test for, I think it's 2 for this one, you do not have to multiply it. You do not have to go in that if you're doing a difference alternative, it will do it in the calculator for you. So whatever your calculator outputs to you is the p-value. You don't have to go through this process. The only time you have to multiply by 2 is when we are doing it by hand. Now, we are at O, making a decision. We've done this many, many times. The p-value is low, you reject the HO. If it's less than alpha, we reject the null hypothesis. If it's greater than alpha, we fail to reject the null hypothesis. Our conclusion is the same conclusion we've been using since one proportion z-test, since our p-value of is either less or greater than our alpha, and alpha is generally 0.05 unless they tell you something different. We reject or fail to reject the null hypothesis. There is or is not convincing evidence that the alternative hypothesis, whatever's happening in your alternative. So we've gone through phantoms. So we are going to get into one by hand, and then I'm going to walk you through how to do one in your calculator. So let's look at our first example. Example 1, a study was conducted on whether time perception, an indication of a person's ability to concentrate, is impaired during caffeine withdrawal. 20 randomly selected coffee drinkers abstained from caffeine for 24 hours. They were asked to estimate how much time had passed during a 45-second time period. The data is displayed below. Do we have convincing evidence, your big signal of a hypothesis test, that caffeine abstinence had a negative impact on time perception, which basically means, does it cause their time to be overestimated? And if there's ever on the AP exam, like something that they're not sure if you're going to interpret correctly, they do usually provide additional information, like they think it's being overestimated, because someone could very easily think, well, a negative impact on time perception could mean that they're underestimating. They stated clearly they're thinking it's an overestimation. So, another thing that I'm noticing before I even get started with the problem, I have data. Typically, if they are giving you a table of data, generally the idea is they want you to enter it into your calculator. So I'm going to go ahead and make sure I have this data in my calculator because they took a sample of 20, which basically means I'm going to have to do a box plot. First thing, define our parameter. Mu is equal to the true mean estimation of elapsed time in seconds. And when it's not as clear, the wording of your parameter is not nitpicky. A lot of the time you can just pull this information from the question, but basically sometimes you just have to figure out what are they trying to estimate. I always like to put in units when I'm doing quantitative data if I can, just because we are dealing with values now and not just counts. So my null, so if everything was perfect and we were in a perfect world, everybody would guess that the time that has elapsed is 45 seconds because that's what happened. So my null is going to be that the mean of everyone's guess would be 45. The alternative, what they think might be happening, is the mean is higher than 45. It's an overestimation. So I have my null, I have my alternative, pH. A is checking my assumptions and conditions. Well, they have said that they randomly selected, so that's good. I can assume that there are at least 200 coffee drinkers in the population. Seems fair. Probably 200 coffee drinkers in your senior class. Definitely. Definitely. So I have my random sample stated. I have assumed at least 200 coffee drinkers in the population. Now I have to go in and do the approximately normal condition. Well, first, they didn't tell me it was normal. Second, they only have a sample of 20. So that means my only option is my third option, a visual representation. So I'm going to go ahead and open up my calculator. And in my calculator, I already have my data, and hopefully I didn't delete any values because I was messing with it this morning. I think I have 20, so I think we're good. Now I'm going to go ahead and graph. So I'm going to do second y equals, and I'm going to turn my plot one on. If you haven't reset your calculator recently and you've graphed something recently, it should already be on. I always like to select the box plot with the dots next to it, only because that means the calculator is checking for outliers for me. So I'm going to hit enter on that. And then my X list is L1, which is what I want. Frequency, we're going to leave it at 1. And then I'm going to do zoom 9. And I see my box plot. So with the AP exam, if for some chance they do have you graph, you have to sketch your box plot onto your paper. So I always hit trace, and then I just go left, right, and take note of the 5-number summary, the minimum, Q1, median, Q3, the maximum. And I put that on my paper. Try to sketch it as closely as you can to the image on your calculator. Now, I know that it kind of looks like there might potentially be a skew over here on the right side of my box plot. However, remember, skew is dependent on distance from your median to your minimum and maximum values. Not kind of what's happening in Q1 or Q3, but is the distance from here to here and here to here approximately the same? So minimum to median, median to maximum. If it is, we can generally say it's symmetric. Basically, no strong skew, no outliers, so I'm going to assume it's approximately normal. Remember that it's very, very important when you are doing this as a part of your answer that you actually write down no strong skew, no outliers, it is approximately normal. Method, one sample t-test. And I went ahead and wrote down my formula. T is equal to x bar minus mu naught over S over square root of n. Now, the one thing that we kind of run into difficulty with these problems by hand when you're doing data in your calculator is you have to get sample mean and you have to get sample standard deviation. So I included this because I do want to remind you, we've done this before. You've gotten a mean and a standard deviation from your calculator just very, very early in the year. So let's go ahead and open back up. Now, if I go to stat and I go over to calc, I can go to number one var stats. It's going to ask me which list do I want it to calculate the statistics for. L1, and we hit calculate. This gives me X bar, this gives me my sample standard deviation, sample size, and if you really wanted your 5-number summary, all of that is in stat calc number 1. So now that we have that, I'm going to go ahead and plug in what I know into my formula. 60.3 was the sample mean minus our null proportion of 45 over standard deviation of 9.8360 over the square root of our sample size 20. When I plug all this into my calculator, I get approximately 6.9565. Now, if you kind of recall how a normal distribution works, we work in terms of standard deviation, and most of our data is within 3 standard deviations of the mean, meaning 99.7% of our data is 3 standard deviations to the left and 3 standard deviations to the right. So when I get a test statistic this large, my brain is already thinking, yeah, this is probably going to be pretty close to 0, if not 0, in terms of a p-value. So I always like to include a sketch. I have my t statistic, and I'm shading everything above it because I'm trying to see if it's an overestimation. I plug this into my calculator, and the way I do that is I'm going to go to TCDF, and let me pull this up and I'll come back one second. Second vars, number 6 is TCDF. It asks you for a lower, so 6.9565. It asks you for an upper, 1E99, and it asks you for degrees of freedom, which is sample size minus 1, so 19. I paste it, and I get 6.255. Don't write 6.255. Pay attention to the very end. It's times 10 to the power of -7. So that means this decimal is moving to the left 7 times. So essentially, our answer is 0. The only time I really write out the scientific notation when my calculator gives it to me is when it's like 10 to the -5. Anything beyond that, I call it essentially 0. The AP exam would be fine with you calling it essentially 0. Sometimes you end up with things like 10 to the -42. That is definitely 0, as long as you include the fact that it is a approximation. Now that we have our p-value, we can conclude, since our p-value is essentially 0, which is less than alpha, very obviously, we reject the null. There is convincing evidence that caffeine abstinence had a negative impact on time perception. You could even say there's convincing evidence that caffeine abstinence caused an overestimation of time, similar to what they said in their parentheses. Now, I always like to do this by hand because often what they will do in multiple choice questions is they will ask you, what's the formula, what's the correct calculation for the test statistic for this problem? Meaning, can you look at the multiple choice answers and determine where each number should be? So it's good to see it. It's good to recognize it because it could be something they potentially ask in multiple choice. They kind of don't necessarily require it in FRQs anymore because most people gravitate towards doing it in their calculator. This is where they kind of go in and make sure, do you really know what you're doing? And that's why they ask it in multiple choice. So I'm going to give you another minute and then we will move on to number 2. I do feel like the hypothesis test gets favored at this point in the year because you've done it more than you've done confidence intervals at this point. Okay, let's go ahead and look at our second example. One company's bottles of grapefruit juice are filled by a machine that is set to dispense an average of 180 milliliters. This is going to be my expectation, my mu naught of liquid. The company has been getting negative feedback from customers about underfilled bottles. To investigate, a quality control inspector takes a random sample of 40 bottles and measures the amount of liquid in each bottle. The sample mean amount of liquid in the bottles is sample mean 179.6 milliliters and the sample standard deviation 1.3 milliliters. Does this data provide convincing evidence at the alpha equals 0.05 significance level that the machine is underfilling the bottles? So, kind of got a lot of information from this question. One thing I'm really happy about is my sample size is pretty large, so I know I'm not going to have to graph anything. I don't have data anyway, so I couldn't graph it if I wanted to. So let's go ahead and first define our parameter. Mu is equal to the true mean amount of liquid in grapefruit bottles. My null is that they are expecting that the bottles should have 180 milliliters. However, my alternative is they think that they are underfilling the bottles. So my null is that mu should be equal to 180. My alternative is that they think the actual mean is less than 180. Then we are going to go through and check our assumptions and conditions. First thing, it was stated as a random sample. And we can assume if they have a sample size of 40, if we multiply that by 10, we can assume that there are at least 400 grapefruit bottles in the population. You could even say in production. N is equal to 40, which is greater than or equal to 30. Therefore, central limit theorem applies. It is approximately normal. One thing to note, you have to include CLT applies, and you have to say, because of that, it's approximately normal. CLT applies, comma, approximately normal. Something on your paper that has both of those statements. Also, you do actually need to check that the sample size is greater than 30. It's something that they want to see on your paper. It's not something that they're just going to assume because you said CLT applies is true. Actually write it out. Method, one sample T test. And so we are going to try this one in our calculator. So the test that we use when we're doing one sample t-test, stat test number 2, we have the option of data or stats, just like we did with our t-interval. Data, I believe, just has you asked, it asks you what L1 is, they ask you about the frequency, and they ask you what your alternative hypothesis is. Stats has a little more symbols. What's the null mean? What's the sample mean? What's the standard deviation? So let's go ahead and open up our calculator. And we're going to go to stat over to tests down to number 2. Yes, for data, they ask you what the null mean is. They ask you where is your data. Frequency, you're going to leave as 1 all of the time. And they ask you what your alternative is. So if you were to do it with data, we are doing it with stats. So I need to enter in my null mean. They are expecting it to be 180. The current mean is, let me double check, 179.6. So let me type it in, 179.6. And the current standard deviation is 1.3. So there we go. And this is just the sample of 40 that the quality inspector took. That's kind of what we're using as our point of reference. Sample size is 40, not 20. And we think that mu is less than mu naught. So I'm going to highlight the second one. And I'm going to calculate. And so my t statistic is negative 1.9460. My p-value is 0.0294. And I always write everything down from my calculator output. That's what we write down on our paper, the entire calculator output. I don't need to see your input, just the output from the calculator. Based on our p-value, since it is less than alpha, we reject the null. There is convincing evidence that the machine is underfilling the bottles.